So today we're going to be starting on electromagnetism. Everything that I cover today will be emphasized by a video that you'll be able to find on my Canvas page by Dan Fullerton. I'm pretty much going to go over the same things that he does. Before we get to the interesting stuff, we need to get the nitty-gritty stuff out of the way. Some definitions, some new terms, some new units that we haven't seen before. And before we get to electromagnetism itself, because as you'll see, as we learn about it, magnetism, you have to have changing stuff. You have to have changing electric fields to produce a changing magnetic field, which will then cause a changing electric field, and that just goes on forever. But in order to really start, in order to get there, we need to first learn about what we call electrostatics. Statics as in not moving, right? So, and when we study electrostatics, we'll be defining some things that will then carry us through the rest of the year. So electrostatics. And I know I say, we're doing electromagnetism. We're not going to see magnetism for quite a while. We're going to be strictly in the realm of electricity for quite a while before we even get to magnetism. Okay. There's the most fundamental unit. It's not the SI unit for reasons that I either forgot or just never really fully understood. But the SI unit for electricity is actually the ampere, which is the unit for electric current. But really the most fundamental unit for electricity is the unit that we use to measure electric charge. And so electric charge, I can't even spell it. Electric charge the symbol, because charge starts with the letter Q, is Q. Sometimes we use lowercase q, sometimes we use uppercase Q. Usually if it's uppercase Q, it's the large charge that's dominating the situation, and then little q will be a smaller charge that's in the same space. What? Yeah. Zap. Yeah. Although that's electrodynamics. But we'll get there too. We'll get there too. The fundamental charge is the charge on a single electron or proton. Obviously, the electron has the negative of that charge, and the proton has a positive of that charge. Okay. Oh, I'm sorry. I jumped ahead. I'm sorry. My bad. I'm sorry. This is Trenton's fault. What do we measure electric charge in? So the unit. Does anyone know?
Volt.
No, that's volt is actually potential. Electric potential.
So what's the difference between charge and potential? Like, is it
we'll learn.
Amps.
Amps is the unit of electric current.
Is it Coulomb?
Coulomb. Yes. It's the Coulomb, which we give a capital C. If you're like me, you wonder why an electron has something called charge, why a proton has something called charge. And the answer is for the same reason that physical objects have mass. It's just an innate property of that thing, right? There's probably more to it than that, but when you get down to it, like, why do objects have mass? I don't know. Why do electrons and protons have charge? I don't know.
Because they are observed to.
Yeah, there you go. Why is one positive and one negative? It was just decided. It was just, that one will say it has positive, and that one will say it has negative, because we know they're opposite. But they could just as easily have said the proton has negative charge and the electron has positive charge. And as we'll see, that would actually have been a better way of describing, of naming the electric charges. Do you know who we have to thank for that? Do you know who?
Histogram.
One of the pioneering scientists who named the positive and negative charges long before Tesla.
Oh, it was the
Dr. Ion.
The gold foil experiment.
No, that was after too. He's more known for being a statesman, but it was actually one of the best scientists of his time, Benjamin Franklin. Yeah. Benjamin Franklin pioneered electrostatics. He was one of the few scientists who did the pioneering work in electrostatics. He's a great scientist. He just was great at a lot of other things too, and so that's what we most known for. Very interesting historical figure. Anyway, so the electric charge, just like the symbol for mass is M, the symbol for charge is Q. Just like we measure mass in kilograms, we measure charges in coulombs. Okay?
Do you spell that Coulomb?
Yeah.
Okay.
Yeah.
That's an amp second, right?
Huh?
A coulomb is the same thing as an amp second?
Yeah.
Okay.
But usually we just call it coulomb.
Okay.
And that's because an amp is coulombs per second. How much charge flows, right? Coulombs per second. So if you multiply that by seconds, then you get coulombs.
We should just start measuring distance in light years for everything.
You can. So the fundamental charge is the charge on a single electron or proton. Obviously, the proton has the positive of this charge. The electron has the negative of this charge. And that gets the symbol E, like electron, right? Lowercase e. And it's 1.6, sorry. Haven't done E and M in a while. 1.6 times 10 to the negative 19th coulombs. One coulomb is a lot of charge. 1 amp is 1 coulomb of charge per second. That can definitely stop your heart. Okay, 1 coulomb is a lot of charge. Okay.
Does that not be confused with the natural number?
Yeah, that is not the base of the natural logarithm, no. But you just look at the context of the situation to know what you're dealing with, right? And usually in a problem, if you're dealing with the equation for calculating electric forces based on charges, you can just use a Q for the electric, if it's a single electron or a single proton. Now, when you get into it and you look at you get deep into particle physics and you learn what actually makes up a proton. Protons are made up of quarks, and so those quarks actually have fractional charges that add up to the fundamental charge. Anyway, the electron, though, is, at least as far as we know, a fundamental particle that doesn't have any constituents that make it up. Okay. Now, charges behave very differently depending on what type of material they are residing on. There's 2 types of materials, 2 overarching types. And those are conductors and insulators. Conductors and insulators. And as you might expect, on conductors, charge flows easily, and on insulators, charge does not flow easily. Now, this isn't like, and when you look at the extremes, yes, you have things that allow charge to pass through them, and you have things that do not allow charge to pass through them. Okay, but that's at the extremes. There's a spectrum there, right? Some things are more conductive than others. Some metals are more conductive than others. Some insulators are more insulating than others. All insulators can become conductors if you have a large enough electric potential difference.
Compare gold and aluminum.
Yeah. Gold is more conductive. It's just that gold is much more expensive. And when you look at like the conductivity per cost ratio, copper is the best. And so that's why we wire everything with copper. That's why when you look at this ceiling fan motor, all these wires here, they're all copper wires. Okay? Because copper is an excellent conductor, and it's relatively cheap because it's in huge abundance in the earth. But there is a spectrum there. This piece of plastic is a very good insulator, but if I get a big enough potential difference, big enough voltage difference across it, then I can get electricity to go through it, and it will become a conductor. Air is an excellent insulator, but you see lightning, so obviously air must be able to conduct electricity, because you see lightning traveling through it. When that happens, it's conducting electricity. So what I recommend, and a lot of teachers don't say this, and a lot of students are confused by this. Why I know that is because I was in the same boat. There's not a strict division between these two. Now, when you look at copper wire versus the like rubber, plasticky cladding that surrounds the copper wire, yes, very different, very different. Copper is on one end of the spectrum. That rubber is on the other end of the spectrum. But you get a big enough voltage and electricity can't actually go through the copper. It just so happens that, for reasons we'll see, I don't want to elaborate further. And for those of you that do get STEM degrees, which is most, if not all of you, you'll learn about thermodynamics when you go to college, when you take your college courses. Things that are good electrical conductors will also always be good heat conductors, right? That's why metal pans heat up a lot more easily. And let's actually talk about it right now. Why is that? What makes a good conductor? What makes a good insulator? Well, insulators are typically smaller atoms / molecules.
Hey, Mr. Graham, does a complete vacuum conduct electricity at all?
Kind of. Not really.
Like,
Kind of.
what do you mean?
No, because you have to have actual charges to actually conduct electricity. But a vacuum, okay, so you're not going to get electricity in a vacuum because you need material through which the charges can actually physically move, but you can have electric fields.
Right, okay.
Yeah. So insulators are typically like polyethylene, glass, things that are rich in carbon, oxygen, a lot of the smaller atoms. Whereas when we think of conductors, we think of metals, right? And metals are larger atoms. And if we just that difference in electrical or material types kind of gives you some insight. If I have a carbon chain, let's just say we have a carbon atom. How many protons are in carbon? 6. So there's 6 electrons, right? This isn't like chemistry class. I'm not trying to be accurate to your chemistry class. And then let's take gold. Someone said gold, which is Au. Does anyone remember the atomic number for gold?
A lot.
It's a lot.
It's 79.
So I'm going to do 7. I'm not going to go all the way 70. There's a lot of electrons, okay? And remember, when you're doing your electron configurations, you feel the orbitals like they're closest, and then as you add more electrons, they get farther and farther away from the nuclei, right? And as we'll learn, there's forces on these electrons due to the positive charged protons, and that's an attractive force. That's called the Coulomb force. You guys know that, right? Opposite charges attract, and like charges repel. You've heard that before, right? You should have learned that before. And so what holds electrons in their atoms? It's the electric force between the protons in the nucleus and the electrons themselves, and it holds them in there. The distance from the protons dictates how strong that force is. And as we'll see today, the electric force is very similar to the gravitational force. It's an inverse square proportion. You double the distance from the source of the force, and you get 1/4 of the force. So when you get more electrons, they get farther and farther out. The valence electrons, the reactive electrons, they get farther and farther away from the center of the atom. Yeah.
I know that the bigger the nucleus, also the stronger the forces are.
That's true. So yeah, this guy has a much larger nucleus, and so it gets a larger force. However, the distance is more important because the distance, it's the square, right? The force is directly proportional to the amount of charge, but the force is inversely proportional to the square of the distance. So the distance from the nucleus is more, it affects the actual force on the electrons more than the size of the nucleus itself.
Why is gold the most reactive, not something like protactinium or something that's a much higher atomic number?
Its position on the periodic table will also affect it based on whether the electrons are valence electrons or not. And then
And it's probably something where like it probably is like something.
yeah, there's going to be something.
It's probably more. It's probably more, but it's also very reactive. So it's like.
So it wouldn't be a good. material to actually use. Yeah, that's beyond the scope of this course. But the bottom line is that these electrons that are real far away from the atomic nucleus of gold, and by real far, it's still really, really close, but if you zoom in, it's a lot farther than these electrons from the carbon nucleus. They're not held on as tightly. And so these electrons are actually kind of free to move around. The outer electrons are free to move around. And so if we have another gold atom here, gold nucleus here, they're essentially sharing. You guys learned about metallic bonding, right? Maybe. One of this guy's electrons can, at one moment in time, be about here, maybe a little closer to this guy, and just jump onto this guy, right? As long as another atom, a gold nucleus, gives this guy one of those electrons. So these electrons, they call it the electron C, right? Or the electron soup, sometimes they call it. Didn't you learn that in chemistry? The electron C? So it's because these electrons, the electrons that are actually part of the C that can flow easily, they're the ones that are farther away from the nucleus, so they're not held on as tightly. Whereas if I have a carbon atom, and I get another carbon atom, there's only 6 electrons there. They're real close. They're held on very tightly. Right? They're held on very tightly, and so they're not readily given up. Okay? And so that's why metals tend to be more conductive, because they tend to have higher atomic number than nonmetals. And nonmetals are what makes up insulators, right? Like the polystyrene and the rubber and balloons, which I think is carbon-based. Glass, which is silica-based. That's another small atom. So that's why. That's it. There's a lot more to it than that. There's a lot more chemistry to that I'm definitely not, super knowledgeable. But I know that is true. Okay.
Apparently that single column of periodic table that has unusually high conductivity of copper, silver, and gold.
Copper, silver, and gold?
Yeah.
Wait, what was the first part?
It's a single column of the periodic table, like down the...
So I imagine there's got to be something there. Periodic table is crazy. There's a crazy amount of information that you can get from the periodic table. It's pretty impressive that they started putting that together hundreds of years ago, too, before modern technology. It's pretty incredible. What was that, Alex?
That was the stuff like electronegativity they showed at the table.
Yeah. Okay. So electric forces. Let's talk about electric forces. All right, we're talking about the electric forces that essentially... And literally everything that you learn about in chemistry is in response to electric forces. Right? Electric forces explain everything about chemistry. All the types of chemical bondings happen because of electric forces. Now, not nuclear forces. Nuclear forces, or nuclear stuff, has to do with the strong and weak nuclear forces. But when we're talking chemical bonds, they're all electric. They're all due to electric forces. Ionic covalent, metallic, the London dispersion forces, the hydrogen bonding forces, those are all due to electric forces, all of them. So everything about chemistry as far as the reactions that proceed because of stuff, it's all due to electric forces. So it's very important, very important. And then we also use electric forces to produce the electricity, obviously, that we all use every day. Okay. So we will write the equation, but there's something that we need to know first. Because Newton's law of universal gravitation, as you'll see, the electric force equation is very similar to Newton's law of universal gravitation. Newton's law of universal gravitation has the constant big G, which is the universal gravitational constant. The similar constant for electric forces is called the Coulomb constant. Which is actually technically expressed in terms of another more fundamental constant, which I'll describe in a second. But it typically gets the symbol lowercase k, because there's nothing else that uses lowercase k in physics or in mathematics. So
Imagine if programmers did that, like they reuse constants.
I imagine that would lead to a lot of problems. A lot of problems.
You just put more letters in the alphabet.
Yeah, there you go. Invent a new one. Okay, so it is actually in terms of another, and you might wonder why we have this, but when we actually start studying electric fields and Gauss's law, and we really start getting into Maxwell's equations, you'll see why it's important. But K is actually 1 divided by 4 pi times another constant I'll talk about in a second, usually referred to as epsilon naught. Not NaUGH naught, NaUGHT naught, not NOT naught. But because this number, 1 over 4 pi epsilon naught, which again, in the future, you'll see why that's important, why this is what it is. But because we use this so much, it also just gets the name Coulomb constant. And so if I actually work this math out, it comes to 9.0 to 2 sig figs, it's 9.0 times 10 to the 9th. And the units are strange, newtons times meters squared per Coulomb squared. This is on your formula sheet. Now, what is this epsilon naught? Timothy actually brought this up, kind of. It's what's called the vacuum permittivity, or aka the permittivity of free space. And once we talk about capacitance, once we learn about capacitors and capacitance, we'll put this in a little more detail. It'll make a little more sense. But you can think of epsilon naught as being a number that describes how readily electric fields can be permitted in free space, in a vacuum. Electric fields can, as Timothy kind of alluded to earlier, exist in a vacuum. And epsilon naught tells you, it's a measure of how readily those electric fields can actually exist in space, or can actually be permitted to exist in space based on the charge that's creating the electric field. Now, if it's not vacuum, objects will still have electrical permittivity. And so you just drop the naught subscript, like this piece of plastic here, right? You can get electric field lines in it. You can get electric fields to I won't say permeate, but to travel through the object, to exist within the object. But this material will allow those electric fields to exist at a slightly smaller amount. Okay? I'll expand on this a lot more once we talk about capacitance, because capacitance is essentially, you can think of do you guys know have you ever heard of capacitors? Do you guys ever heard of a guy named Michael Faraday?
Yeah.
So Faraday, excellent, very interesting historical figure when it comes to the history of science, because Michael Faraday came from very lowly origins. He was a peasant, and who just worked his way up to the highest levels, and when he died was one of the most well-known scientists. And not only that, but he also gave what are now known as the Christmas lectures, where he would lecture to the public, and the public would come and be awed by what Michael Faraday had figured out. Very interesting historical figure in the realm of science. But because of his work, he got the unit for capacitance named after him. And capacitance is literally how much charge you can store, right? You can think of it kind of like a battery, right? You store charge on a capacitor. And so you can store charge. You can store charge which create electric fields in space. You can create electric fields in space by storing charge. And so permittivity is measured in farads, which is the unit for capacitance per meter, farads per meter. And so that'll make a lot more sense once we start learning about capacitors and capacitance. But anyway, epsilon naught has a value.
Wait, do batteries technically store charge? Because if you're if you run the current through them to charge them, isn't that basically converting the molecules?
Overall, batteries are neutral,
Right.
but they sequester the charge
Right,
through chemical reactions.
There's a potential difference, but isn't it storing it as chemical energy rather than an electric charge? Am I wrong on that?
Well, the chemical energy is used to produce chemical energy is used for it. There's a transfer of chemical energy in the chemical reactions that separate the charges.
Sure, but is it storing a charge in the sense of an electric field?
Yeah, yeah. There's definitely, yeah.
Okay.
And something that we'll study in this class is batteries, for sure. Yeah. Just not so much of the chemistry part, because again, I don't know much chemistry.
I think you did
Yeah, I did a lot of batteries.
in AP Chem?
Yeah.
Okay. Okay, so epsilon naught is 8.85 times 10 to the negative 12. And because it's in the denominator where K is in the numerator, it's simply the inverse of this. So it's Coulomb squared per newtons times meters squared. And again, dimensionally, this unit is the same as farads per meter, which is the unit of capacitance. So it's the ability to store charge, which creates electric fields per meter of separation, which we'll talk about when we do.
So that
Capacitance.
is a Coulomb squared over Newton times meters.
Yeah. Okay. And again, it's let me write this because this is in my notes. So epsilon naught, this number, the vacuum permittivity, is the definition is a measure of the capability of a classical vacuum. How do you spell vacuum?
Is that a hint where that's not really how it works?
What's that?
The classical vacuum.
Yeah.
Is that a hint that it doesn't really work?
Yeah.
Like that? Okay.
Yeah. To permit electric field lines.
So beyond the scope of this,
No, it's definitely, except in extreme cases, it works fine. Whenever you hear classical physics, right? Newtonian mechanics is classical physics. Some scientists even think of relativity as kind of being classical physics because it's kind of like you learn relativity. We hear relativity in Einstein, we're all, yeah, that must be hard because Einstein was real smart. If you get a physics degree undergrad, you know relativity very well by the end of that degree. Probably not as well as Einstein, but you know relativity. But really, when you say classical physics is everything before the early 1900s, modern physics is with the addition of relativity and quantum mechanics. But yeah, in most cases, just like you can use Newton's laws, you don't need relativity if you're sending something to the moon, right? That's even that's a pretty extreme situation, but really that's an everyday situation. You don't need relativity unless you're talking about the discrepancy in the orbit of Mercury because it's so close to the sun. Or you're talking about an object in a particle accelerator that's traveling 99% the speed of light, right? You don't need relativity until you get to those extremes. So in the vast majority of cases where we're dealing with electromagnetism, a classical vacuum, it's fine. It's fine. Why a classical vacuum? Because a classical vacuum is just nothingness, right? It's just empty space with nothing there. Once you learn about quantum mechanics, you know that there's stuff going on in nothingness, right? Empty space with no atoms, even no radiation, no electromagnetic radiation, just a region of space that's completely empty and devoid of anything. There's still stuff going on there. There's still energy there. And so that's when you get out of the realm of the classical vacuum into the modern conception of a vacuum.
so what happens in this?
Oh, a lot of weird stuff. Ask Joel. He'll tell you after class. Okay. So with that information, we can write Coulomb's law. And you can write it in two different ways. With either K or with 1 over 4 pi epsilon naught. But it turns out that and I'm going to draw two charges here. Now that it's very similar to gravity, but whereas gravity is always an attractive force, the electric force can be attractive or repulsive, as we know, right? Like charges repel, opposite charges attract. So do you want them to attract or repel? You say, I don't care. Attract.
Oh, dang it.
So I'm going to have a positive Q and a negative Q. This could be a proton electron. This could be a ball of positive charge, a lot more than just a single proton. This could be a ball of negative charge, a lot more than just an electron, a single electron. And so I'll call this Q1, Q2. And say they're separated in space by a distance r. If I wanted to be technical, I would say I would define a coordinate axis where that's my y direction, this is my x direction, and then r would actually be a position vector, right? Indicating the position of one object in relation to the other. Remember we did that with the gravitational force, and that's why we put the negative in front of big G m1 m2 over r squared, because if I'm measuring from this guy and r is this way, the gravitational force will always be the negative, in the negative direction of r. So, but if I'm just talking about magnitudes, which I think is how it's written on the formula sheet for the electric force, yes. First of all, the electric force, which I'll put Fe, is directly proportional to the product of the two charges. Just like the gravitational force is directly proportional to the product of the two masses. Very interesting how nature is kind of similar in this way. The electric force is also inversely proportional to the square of the separation of the two charges. Oh boy, I hope I can flip that after recording. I forgot to flip it before I recorded it. I can do that, right? And so this is the proportion. So to make an equation out of this, I have the proportionality constant. It turns out that K is the proportionality constant, which was experimentally determined and then was later determined to be essentially a property of this vacuum permittivity. And so it can be expressed in that way. So we can either write it as the magnitude of the electric force, and then you just need to use your knowledge of whether they're both negative, both positive, or one's positive and one negative to determine the resulting direction of the force is equal to K times Q1 times the magnitude, yeah. Because regardless of what direction, regardless of what signs, what charge signs the charges are, again, you just use your knowledge to say whether they're going to be positive or negative. So I could write it like this, but then I could also write it, and this is the way it's written on the formula sheet. Because for most purposes, you could just use K. You can say 9 times 10 to the 9th, right? That's the proportionality constant. Or you can write it the big kid way, which we'll end up doing whenever we get into Gauss's law and some more complex field stuff. It's 1 over 4 pi epsilon naught times the magnitude of Q, the product of the two charges, divided by the square of the distance. So that's what's on the formula sheet. Just get it right here. And note, it's essentially the proportionality constant times the product of the two charges divided by the distance between them squared. I can write the gravitational force in the same way. It's big G times the magnitude of the two masses divided by the distance between them squared. It's Newton's law of universal gravitation. Okay. It's very similar.
So since it's magnitude, it basically proves that there's antimatter then, right? If you're considering.
No, when we're talking magnitude here, okay, I see what you're saying. Yeah, that's why typically we don't do that. But yes, antimatter is a thing, but I don't think that really is involved here. The thing I like pointing out, though, is that you learn about the 4 fundamental forces in the universe. You got the strong and weak nuclear forces, you got the electromagnetic force, you got the gravitational force. Every force that we encounter is one of those 4. Most of them are electromagnetic forces that we encounter in our everyday lives. Gravity is by far the weakest of the 4 fundamental forces in the universe. And that is kind of, and we're talking like pound per pound, like strength, pound for pound strength of these forces. G is 6.67 times 10 to the negative 11th. K, and that's newtons times meter squared per kilogram squared, right? That's what G is measured in. K is measured in newtons times meter squared per coulomb squared. That number is 9 times 10 to the 9th. So pound for pound, the electric force is a billion million times stronger. I think that's what it was. I think it was 4 billions and a million. A million billion. Maybe just 3 billions. I don't know. But it's significantly more stronger than the gravitational force.
So what Logan just said made me think. So like, you know how with like the ideas of gravity and stuff, they have like the net with like stuff and it creates like a whole bunch of stuff. Would that mean antimatter would like pull it up?
No, antimatter still attracts just like normal
I
matter.
was just like, yeah.
Yeah, antimatter has like opposite charge. Like an antiproton, anti-electron is a positron. It's like an electron with a positive charge. But it still behaves, as far as gravity goes, it still behaves like.
Oh.
But the amounts of antimatter that any scientist ever deals with are so small that the gravitational force is completely ignored because it's negligible compared to the electric forces that are actually, actually seen and used and studied. Good question, though. So that's why you need something the size of the Earth just to keep us stuck to it, right? You don't need a lot of charge in order to produce huge electrical forces. You need a lot of mass to produce huge gravitational forces. A lot of mass. Okay. Okay, so, and again, this guy here can be attractive or repulsive. All right. So before we get on to the next stuff, let's just get some visuals. Let's see electrical forces in action. So I got a couple. There's some experiments that you can just do at home. It turns out that when we have the atoms that I erased here, when you think of even insulating atoms as holding on to their electrons tightly, they don't always just, you can still take those electrons off. You guys learn about ionization energy, right? Like you pass electricity through a gas and you can kick electrons off. Right? You can kick electrons off. And typically those electrons, I can take electrons off of, here I got 2 pieces of tape. Sorry, I'm getting ahead of myself.
Is that like when you remove rust through electrolysis? Is that what you're talking about?
No, it's even simpler than that. No chemical reactions required. So here I got 2 pieces of tape stuck together. And when I separate them, one of them is going to pull electrons off the other one. The least strongly held onto valence electrons is going to pick up some of those electrons. So one of these guys got positively charged while one of them became negatively charged. The one that took electrons became negatively charged. The one that gave them up became positively charged. And so when I hold these guys close together, you can see the attractive force. Right? They get attracted to each other. So even though these are insulating atoms, again, you don't want to get into the mindset that insulators do not allow electrons to move and conductors allow electrons to move. Even insulators can allow electrons to move. The thing is you got to put in some energy, right? You got to put in some energy in order to move those electrons. You got to do, it literally comes down to you got to do work, right? Where was the work? I did the work. I exerted a force over a certain distance to separate these 2 guys, and in the process, electrons got ripped off of one and added onto the other. And so I get the opposite charges attract. Now, what I can also do is charge these guys in a very similar way. If I put them both on the table, normally we would do this as a little lab activity, but since we can't do labs anymore. So I'm gonna neutralize them, right? I'm gonna ground them to try to get rid of all that excess charge I put on it. But now I'm gonna rip them both off of the table. Now, one of those is going to rip electrons from the other one. The table might get electrons from the tape. The tape might get electrons from the table. In order to know which is which does it, then we have to, I'll show you that in a second. But I'm going to charge these 2 objects. Notice I charged them before by ripping electrons off of one and putting them onto the other. Here, I'm charging them both in the same way. So now they should have the same type of charge, so the objects should do what? They should repel. Which they do. Right now they're not attracting, now they're repelling. So what you've just seen is what's called charging an object. By charging an object, you're either taking electrons off of it or you're putting electrons onto it. Okay? And the thing is that obviously every material in the universe is made up of countless numbers of electric charges, right? This regulation size hockey puck right here has uncountable trillions and trillions and trillions of electrons and protons, right? Just uncountable. But overall, it's neutral because the amount of electrons matches the number of protons. When you charge an object, and I'm going to say that for the remainder, you'll be saying that for the remainder of this year and beyond. When you say you're charging an object, you're not bringing electrons into existence. You're not bringing protons into existence. All you're doing is transferring electrons from one material to another. Okay. So if you take electrons from one off of a material, it becomes positively charged because now it has more protons than electrons. If you add electrons to a material, then it becomes negatively charged because you're adding electrons, you're adding negative charges. Right?
So whenever you put on a hoodie, is that like basically the hoodie like taking some electrons with it?
When you feel like the staticky?
Yeah.
Yeah. And we'll learn, I'm just going to show you a couple other examples here. Oh, I don't want to do that. This is one of my favorite ones. Here I got a little plastic grocery bag, right? Produce bag that I've just cut a loop out of. And this is my old pet, Fluffy. It's actually rabbit fur. Rabbit fur is very, very good at taking electrons off of objects. So I'm just going to rub this piece of plastic. I'm going to rub this balloon. What time is this class in?
11:03.
Oh. Okay, we're going to have to wait till tomorrow to really get in the nitty gritty here. So now I'm charging this balloon and this loop of plastic in the same way. And what you'll see is that they both become negatively charged, if I remember correctly. And so they should repel now. And they do.
Well, if it takes electrons, wouldn't they be positively charged?
I forget if it's taking electrons or adding them on. I'll have to look at. There's a table that we'll learn how to read. But see it, so they're repulsive now. Now what's interesting is the ceiling is neutral, and yet that will stick to the ceiling. Just like this wall is neutral. If it wasn't, then it would shock me, right? Like I get a shock from a doorknob when I touch it after I've rubbed my feet on the ground. When you rub your feet on the carpet, you're charging your body. And then when you touch the doorknob and you get a shock, you're discharging, right? You're getting rid of that excess charge. The wall here is electrically neutral. If it wasn't, it would shock me when I touch it. The wall is electrically neutral, and yet I still get a charged balloon to be attracted to it somehow, for some reason.
Is it big enough difference in charge?
What's that?
Is it big enough difference in charge for it to attract?
No, the wall is neutral. The balloon is not, but the wall is. And so your homework for tonight is to watch the video from Dan Fullerton on my Canvas page. Okay? It goes for you guys at home too. The homework is to watch that video, and then it'll explain why this happens, and tomorrow I'll elaborate on it. I think it's like a 15-minute video, so just watch that. No other homework for tonight. And that'll be it. Yes, I'm making you do school.